And now on to the second part, to part 2 of angular motion examples. We have the following problem. You have an 8 kilogram bar, 1 meter long, kept in horizontal position by two strings attached at its ends. You have the left string and the right string as shown in the figure. A 2 kilogram object is placed on top of the 8 kilogram bar. Determine the tension in the left string. In this particular problem, no pivot point has been specified. Some problems will specify the pivot point, in which case you must use the specified pivot point to analyze and answer the problem. But in this case, no pivot point has been specified or mentioned, in which case you are free to choose the pivot point that you will use to analyze the system. So let's say we use the right end of the 8 kilogram block as the pivot point for our analysis. Let M1 be 8 kilogram, M2 be 2 kilograms, let 1 meter be L1 and 0.8 meters be L2. First thing you need to do is identify the forces that are acting in the system. Clearly, we have M1 and M2, we have masses, therefore we have weights. We have weight 1 and we have weight 2. The system is supported by the strings, therefore there are tension in the strings. Tension in the left string, let it be T1, and the tension in the right string, let that be T2. The system is just suspended in place. It is static. So static case or static equilibrium. The system is in a state of equilibrium, therefore the net torque is equal to 0. By definition, net torque is summation of the individual torques of the forces present in the system. So you have torque of tension 1 plus torque of tension 2 plus torque of weight 1 plus torque of weight 2 equal to 0. Applying the definition of force and its lever arm, torque is equal, you will recall torque is equal to force multiplied by its lever arm plus minus, plus if in the positive direction, minus if in the negative direction. So applying that definition, we get the torque of T1 to be minus T1 dt1. Torque of T2 is 0, considering that T2 is applied on the pivot point. Torque of weight 1 is weight 1 multiplied by d weight 1. And torque of weight 2 is weight 2 multiplied by dW2. Taking note again that the pivot point is chosen to be on the right end of the 8 kilogram block, we determine that the lever arm of T1 is 1 meter. The lever arm of weight 1 is 0.5 meters. And the lever arm of weight 2 is 0.2 meters. Isolating the tension in the left string, T1, we see that we are able to calculate T1 to be 43.12 newtons. Let's go now to the next example. Starting from rest, at the top of a hill, a sphere rolls downhill. The sphere has a mass of 1 kilogram and a radius of 0.5 meters. If the hill has a height of 8 meters, determine the linear speed of the sphere at the bottom of the hill. Let m be the mass of the sphere, 1 kilogram, and r be the radius of the sphere, 0.5 meters. Initial position is at the top of the hill and final position is at the bottom of the hill. Therefore, h initial is 8 meters, the height of the hill, and final height h is equal to 0 at the bottom of the hill. It's always good practice to set the lower level to 0. The sphere started at rest. Therefore, in terms of linear motion, initial speed is 0. In terms of angular motion, initial angular velocity or initial angular speed is 0. For this problem, we look at the energy of the system. Conservation of energy tells us the following. Initial energy is equal to final energy. In terms of kinetic energy and potential energy, we have initial kinetic energy plus initial rotational kinetic energy plus initial potential energy plus work done by external forces, if any, is equal to final kinetic energy plus final rotational kinetic energy plus final potential energy. The rolling sphere is experiencing both linear motion and angular motion. Therefore, it has both linear kinetic energy and angular or rotational kinetic energy. Initially, at the top of the hill, the sphere is at rest. Therefore, initial linear kinetic energy is 0 and initial rotational kinetic energy is 0. At the bottom of the hill, the final kinetic energy is 1/2 mv squared, while the final rotational kinetic energy is 1/2 I omega squared. A rolling sphere is basically a sphere that is rotating or spinning about an axis through its center. So the moment of inertia of the sphere is 2/5 mr squared. V and omega are related together. V, the linear speed v, is also equal to the tangential speed of the sphere. And from our kinematics, we know the relationship of angular speed and tangential speed. Omega is equal to v over r. Combining these equations and simplifying, we see that we are able to determine the final speed of the sphere when it reaches the bottom of the hill, 10.5830 meters per second. And now we have our last example. A skater is spinning like a top. With her arms down, her moment of inertia is 1.9 kilogram meter squared. And she is spinning at a rate of 15 radians per second. She brings her arms up, which changes her moment of inertia to 3.8 kilogram meter squared. Determine her work done in bringing up her arms. In bringing up her arms, she changes her moment of inertia from 1.9 to 3.8. So we have I initial and I final. The skater's initial angular speed, omega initial, is 15 radians per second. Using conservation of angular momentum, L naught is equal to L. We have I initial, omega initial is equal to I omega. And we are able to determine the final angular speed of the skater to be 7.5 radians per second. So from 15 radians per second, the angular speed changes to 7.5 radians per second, which means the rotational kinetic energy changes. We are able Then, to determine the work done in changing the rotational kinetic energy, the work done is calculated to be negative 106.875 joules. And with that, we are done with the topic of angular motion. Thank you for watching.